In this session, we'll be talking about creating an ARIMA model for time series analysis and doing some kind of basic forecasting works using the ARIMA models in R. So the basic is you should really have a decent understanding of what an ARIMA model is. Auto-regressive, integrated, conditionally heteroscedastic model. Moving average. Auto-regressive, integrated, moving average model. So we are doing the time series modeling using the ARIMA model, and once a appropriate ARIMA model is created, we will be getting into the forecasting for the future for that particular data. So it's one of the important class of linear time series models, right? Whenever we have a time series data and if I have to model it, this is one major category of models. This is also called as a Box-Jenkins kind of model because it is typically named after the person who has really proposed this kind of a model. And we need to understand some of the basic things here. Whenever we have the current value depending on the past values, right? This kind of models we use whenever we have an impression that the current values are dependent on the past values of that same time series data or the past values of the error term. So basically it is like the current value, the today's value, let's say I'm talking about the today's price, it should be dependent either on the previous prices. So yesterday's price, the last month's price, like that. The previous prices or the previous error terms. When I say error terms, the difference between the predicted value and the actual values of the past. So that is what we are calling as the error term. So basically we are saying these ARIMA kind of models, they assume that the current value, whether it is a price or returns or whatever it is, the current value is dependent on the previous values of the same element or they are also dependent on the previous error term. That is what is the scenario where we are going to use the ARIMA category of model. So here we talk about three stages. One, from my historical data, I should be able to identify an appropriate model. So when I say identification here, I am basically determining the order of the model. So how many past values? So basically I have to find out the number of past values on which my model, the current value is depending, and also the number of past error terms the current value is dependent upon. So this is what is the model identification process. So when I am talking about the number of past values, this is to do with the auto regression term, AR term. And when I am talking of number of past error terms, this is to do with the MA, the moving average part. So I have to identify what is the order of the model. So that is my first step in any ARIMA modeling. And based on that, I have to come out with an estimation, right? Estimation of the parameters. So when I say parameters, okay, I have identified that the past 2 months values. So current month is dependent on the last month, and so the current month T is dependent on the value T minus 1 as well as T minus 2. Then how much weightage should I give to T minus 1? How much, what should be the weightage I should give to T minus 2? These are what I am calling as the parameters. So I have to estimate the parameters of the model. And in general, the parameters of the model are estimated using either a least squares mechanism, either the least squares approach, or we can use the maximum likelihood approach. So different cases we can use different kinds of approaches to estimate the parameters. We know that when we are in regression kind of an exercise, we'll use the ordinary least squares mechanism, and when in some cases where we don't have the dependent variable, we can even look at the maximum likelihood based approximate estimation mechanism. So the first step is I am looking at the order, right? And for the order, I can use different kinds of mechanisms again. When I have to determine the order, I can use either a graphical method to find out what is the order of the model, or I can very well use information criteria. We'll see when we are actually implementing it in a practical way. We'll use what is called as information criteria. Two major information criteria: AIC, which is called as Akaike's information criteria. Then we also have BIC, which is called as Bayesian information criteria, or the same thing is called as Quartz information criteria. So one of these criteria is typically being used to identify the best possible kind of a model, and for that particular model we are going into the estimation of the parameters when we are building an ARIMA model. And the third stage is the diagnostics. So we are actually checking, we are very much checking the model that we have got created in the step 1 and step 2. I have to really check whether it is adequate, whether it is sufficient to do the forecasting. So basically what we really look out here is we look out for the residuals. We see whether the residuals are behaving as a white noise or not, which means the residuals, the error terms that are coming up, they should not have any kind of dependence within the residuals. The residuals are completely independent of each other. So that is what we do as a part of the diagnostic checking exercise. So that's one more thing we have to make sure when we are going ahead in terms of doing a ARIMA based modeling of the time series data. So we'll try to do these 3 steps on a data set. We'll take a data set, we'll try to implement all these 3 stages and try to use the model for the forecasting purposes. And for this, I suggest that we use Forecast, a package called Forecast. You install the package called Forecast. So let's implement, let's start R. Okay. So let's install a package called Forecast. I'm installing. I'm selecting India, and here is where I'm installing a package called Forecast. Okay, I'm installing a package called Forecast. So this package is installed successfully. So let's let's load that particular package. So I'll say library forecast. So when I'm using library forecast, that particular package is typically loaded. Okay. So now this is where we'll use a data set. Let me see what data set I can use. Right. Let me go to my data files. Okay, let me use this Sensex monthly data set. Let me open the data set for you to see what it contains. Okay, it contains the months, right? 2001, 2002, 2003, which is year is 2001 is the month, and both are separated by a slash. And we have data until 2016 April. So this is the kind of a data that we have, and this is the monthly closing values of the Sensex. So let me call this as Sensex. So this is the monthly closing values of the Sensex. So this is the simple data that we have. So this data let's read into R. This is in the Excel sheet. So let's read this data into R. So for that I'm calling some variable. I'm creating a variable called Sensex monthly. And you remember we have used read.zoo. So read.zoo is a kind of a time series reading function. So I'll be using the data which is present in my E drive. R data is the name of the folder, and I have my data as Sensex monthly .csv file. So this is my data. So I want to read this data. Now because it's a CSV file, obviously my separator is a comma, and this has a header, right? The first row is having a heading month and Sensex. So that's where I'll mention header equal to true. And the format of the time series I have to mention. In read.zoo I should always mention the format of the time series. So that's where I am mentioning format equal to, what is the format here? The full year, which is a capital Y format. So I'll say percentage capital Y, and then I have a slash, and it's in a month, which is a small m. So percentage m. So this is the kind of a format. So this format I have to enclose in quotes. I can keep this format in double quotes. Then how do I really want this function to be read? So I will keep it as year and month kind of a format. So that's where I'll say fun. Fun is nothing but the function. I say as dot year month. Means I want this function to be read as years and months. So this is the name of this is how we are reading the Sensex monthly data from a CSV file into R. Let's check how it has come. I'll look at head of Sensex monthly to see what has really come out. Yes, you see here it is coming out as Jan 2000 because we have kept the function as year mon. If I had not mentioned it like this, I would have got it in the traditional format. So here, because I have mentioned the function as year and month, so I am getting the month name followed by the year number. So these are the values associated, and this is what is contained in Sensex monthly. So the main purpose of using this function argument is monthly data points. So the data point that I require are the monthly. So the date column actually looks at the monthly values only. Basically the thing is, if you look at frequency, if you look at the frequency of the same, it will give it as 12, which means this data is having, so this is what we really require when we have to talk about the seasonality present in the data. monthly seasonality, if I have to look at, I should always use the function as dot year month. Okay, now I'll simply go ahead in terms of using the ARIMA model. But yeah, let's see, we'll use the ARIMA model on the returns rather than on the prices. We will use the ARIMA model on the simple return. So just to recollect the returns, we have a mechanism to collect the returns. So let me call it as return simple. Right? How do we compute it? I'll first take the difference P2 minus P1. So I'll take the difference of Sensex monthly and I divide it by P1, the lag, 1 period lag. So I'll say period lag Sensex monthly, where I'm putting 1 period lag, so K I'm setting it as -1. And this I'm multiplying it with 100. So just if I have to see the head, the first 6 values of the simple return. So I'm getting, for the January month I'm not getting, because obviously that's the first, and P2 minus P1, the previous value is not available for that month. So we are not it is not getting calculated for the month of January. So this is the February return, 4.64%. In the March there is a loss of 8.18%. There is a loss of 6.87%, and so on. So these are what are the returns that are coming up. Now I really want to use ARIMA model, auto-regressive integrated moving average model, on my returns data, simple returns data, right? And this is where I would be using the forecast package. That is the reason I have asked you to install the forecast package. The forecast package actually has a very interesting function called auto.arima. Auto.arima is a very interesting function which actually identifies on its own an optimal model. So the best possible model, right? When I'm saying identifying the best possible model, the number of previous values and the number of previous error terms which are required to estimate the current value. So it will do the first step, optimal model identification, and along with it the second step also, which is the estimation of the coefficients, parameters. So these two are done in one single step. So that is what will bring in the advantage. Even we really don't need to execute one after the other, but in one single shot we can go ahead and implement the entire model, get the best possibly fitted model, and based on that use that model for the prediction and the forecasting purposes, right? So let's go ahead in terms of the ARIMA model. So I'll take some variable called mod, where I'm using the function auto.arima. Now that we have already loaded the forecast package, the auto.arima function is available to it. So the first I have to mention what is the data, what is the name of the data which contains the model, for which I have to create this kind of a ARIMA model. So Sensex monthly is the name of the data for which I have to create the ARIMA model. Then yeah, right now we will restrict this model to only stationary models. We have already discussed what a stationary model is. So we will restrict our analysis only to a stationary model, which means here I am assuming that the Sensex monthly, oh no, I'll not use it on Sensex monthly, I'll use it on returns. So I'll use it on ret underscore simple, right? I'll assume that the stationarity, so for that I'll use a variable called stationary and I'll say it is true. right? One of the, so you can very well query question mark and auto.arima, where it will show you what are the various functions or what are the various arguments that go into that particular function. So whenever we are trying to find out auto-arima, the first thing I'll specify is on what data I am trying to do an arima, what is the level of stationarity that is present in the data. So am I assuming that the data is more and more stationary, or is it not stationary? Then we can also check out whether we want to look at seasonal models also, seasonal decomposition also need to be considered or not. Generally, per case of stock prices and all, we don't see any kind of seasonal patterns in the data, so we can very well ignore the seasonality part. But if we talk about some sales prices or sales values, then I should very well set seasonality to true, because there could be some kind of seasonal behavior present in the data. So seasonality here I am setting as false. And if you remember the models for identification, the best model, we said either I can use a graphical model or we can use an information criteria to identify which model is the best. And within that there are two major criteria, AIC, which is the Akai case information criteria, or we also have a Bayesian information criteria. So here I am using the AIC as a differentiator. So I am simply setting IC, which is the information criteria. Here I am setting it as AIC. So this is how I am simply writing the piece of code. Right? It's a this AIC is a kind of a measure of which model is the best for me. So on what basis the model selection is typically being made. Here the model selection is being made based on the Akai case information criteria. So this is how we have got our ARIMA model created for this particular data set. So if I really want to see what this model, what is the best fitting model for this data, I can simply say mod, which is the name of this particular fitted model. Oh, this is an ARIMA 000 model. Okay, there is no dependency on the past values, zero dependency on past values. There is also a zero dependency on the past error terms also. So there is literally no dependency at all. So the current value is completely independent of the past values. The current return is completely independent of the past return. Oh, so this is nowhere an ARIMA model. ARIMA model is nowhere suitable to fit to this kind of a data. So okay, so let me try something else for you, right? Just let's try to understand something more. Here we have used the data right from 2000 to 2016. So that's where probably it might look that the ARIMA model is not that perfectly fitting. What I'll do is we'll take the data only from, let's say, 2011, right? 1st Jan 2011 to 31st December 2015. Let's only take the data only up to this part, and let's see if we can fit any kind of an ARIMA model based on the last 5 years data. So I'll simply use another variable, right? Sensex 2011-15. That's the name of the variable I'm simply using. So we'll do a shortlisting. So that's where I'm using window as a function to shortlist from the original. So original data is Sensex monthly. Out of this, I'm specifying the start date. So I'm saying start, and if you remember the time series data, the start has to be given in YYYY 2011 hyphen MM, which is 01 hyphen 01 date. That is my start. and my end is, again I should give it in the same way, 2015, 12, 31. So I'm taking a subset of my original data and I'm storing it under Sensex 2011-15. So this is my new data set. So for this new data set, I want to find out the return. Right? I could have done the returns directly on this data set itself. Yeah, we'll do that. Instead of taking the data directly from 2010, let's take the returns from 2011 onward. So what do I do instead of Sensex monthly? We'll take red simple directly. So this will take over the last 5 years. And for this, let's try to fit the ARIMA. Right? For this data, let's try to fit the ARIMA. So which means I am not using red simple here. For fitting of ARIMA, I'm using Sensex 2011-15. Okay, so now when I look at the mod, even here also the mod is 000. Okay, let me try fitting the ARIMA on the prices itself, which is Sensex 2011-15. We'll take the price, right? Instead of so I'll take the 2011-15, I'll take it as on the Sensex monthly. I'm taking the start from 1st Jan 2011 to 31st December. So I'm taking the prices, values, rather than the returns. Let's see how it works. And on the top of it, let's build a model. Okay. So let me see what is the mod now. Yes, here at least AR1 is coming up. So this is the ARIMA 1,0,0 model. So which means the past value, one past value is current value is dependent on one past value. So what is that we have modeled here finally? The price. The price at time period T, it is dependent on AR1, which means it is dependent on price at time period T minus 1, but it is nowhere dependent on any other error term. If it had been dependent on any other error terms, we could have got MA as a part of the model, which means this particular number would not have been 0, it would have been a non-zero term. Right? So here this is coming out as ARIMA 1,0,0. So the first term is associated with auto-regression, the second term is associated with integrated, and the third term is associated with moving average. So here it is showing 1,0,0. So which means I can very well identify this as a AR1 model. So for this particular data, it is looking like AR1 model is the best fit based on the Akai case information criteria, where the AIC value is 995.04. That is the best possible value that could come out, which had given me AR1 as the model. Right? So this is the best possible fitting model for this particular Sensex 2011-15 kind of a data. And the best way to identify the same also is you go with a ACF, which is an auto correlation function. It's a kind of a plotting that we can do. ACF plot is something that we can look at, which is an auto correlation function to really get a graphical understanding of the same. So I'll do an ACF of Sensex 2011-15. So when I'm doing the ACF of 2011-15, I could see that the correlation with respect to the first one is much higher, almost very highly dependent, and after that we see that there is a gradual fall in the correlation function, auto correlation value. And the same way, if I look at the PACF, which is the partial autocorrelation function. That is something which will really give me what model is suitable. So let's try looking at the partial autocorrelation function. Very clearly it is showing that only at lag 1 there is a heavy level of dependency, whereas after that the levels of dependency have completely died off, right? So it is almost zero kind of partial autocorrelations from lag 2 onwards. Only at lag 1 there is a very significant non-zero partial autocorrelation. So that means it's an order 1. Autocorrelation of order 1 is more and more appropriate for this data. And just for you to check out, probably if we try PACF on the return simple, right, we got that it's a AR0 model for that. So if you look at the PACF, you see that all of them are much within this dotted line. Anything that is crossing this dotted line, that correlation is very significant. Whereas here you see none of the partial autocorrelation functions are significant. That's where when it comes with respect to the returns data, it came out that the order of the autocorrelation is 0. So whereas, the order of autoregression is 0. Whereas here it is coming out that there is an order of 1. And if you look at the coefficients here, yes. So what do I write it based on this? I can very well write here the equation. I can write it as the price at time period t is same as it can be modeled as the intercept 21,921.888 plus 0.9759 times the price at period t minus 1. This is what is the best possible model that has come out through this auto.arima function. So the intercept, which is more or less equivalent to the mean. The intercept is more or less equal to the mean. And if the model contains an AR term. And if you look at, these are the standard errors that are associated with each one of them. Here you could see that the standard error is significant, right? Here the standard error is significant at the 5% level, because this value is much lesser than 0.05. Or we can very well go ahead trying to identify the confidence intervals associated, right? So I can very well say conf interval associated with the same mod. I'll look at the confidence intervals. So this is showing the minimum value is 0.93 and the maximum, the 2.5% is 0.93 and the 97.5% is 1.01, which means the 95% confidence interval is that parameter lies between 0.93 and 1.01. So the confidence interval does not contain a 0, which means this the value, the coefficient of AR1 is more or less significant at 5% level, right? So that is how the ARIMA model is getting created. Here our ARIMA model is typically a AR1 model. And now once my model got created, I can very well validate the model. And the best thing I say if I have to validate the model is I can very well plot the time series diagnostics. Right, I can very well look at the time series diagnostics to come out with a validation of the model. So for that I'll use a function called tsdiag, which is the time series diagnostics of my model. So there are three things that are coming out here. One, look at the ACF of the fitted value of the model. Except for a lag of 0, nowhere the autocorrelation function is above or below the limits. Similarly, look out for the p-values. The p-values are also much higher than 0.05 across, which is a clear indication that none of the values are significant. So there are three things that you can look at. One, look at your standardized residuals. There is no kind of a clustering in your standardized residuals. There is no volatility clustering where or at some periods the volatility is very high, at some periods the volatility is very low. Such kind of clustering is not found, right? Now autocorrelation wise, only at time period time lag of 0 something is significant, but after that I am not able to see any kind of significant autocorrelations in the residuals. So there is no dependency in the residuals at any point in time. That is what is an indication of a good model. And even as a part of the statistical testing, which is the junk box statistic that is computed for autocorrelation, all the p-values are greater than 0.05. So here the null hypothesis for the junk box statistic, the null hypothesis that we typically make is residuals are independent. Right? The junk box statistic typically makes a hypothesis that the residuals are independent, which means the alternate hypothesis is they are not. And since the p-values are much greater than 0.05, I will not be able to reject the null hypothesis. So I can very well, using the junk box statistic, also say that the residuals are more or less independent, right? So we can even look at a simple graphical mechanism also. We'll first plot the actual values, and on the top of it let's try to fit our fitted values. So first let me take from this mod, right? I'll take from this mod the x value. So if you look at this mod, what is there as a part of my mod x? Okay, these are the values that we have. So I'll take from the mod, I'll take my x values. So let me do a plotting of the actual values. So which is mod $x. So from this mod, which is our output that we have got, I'm taking the actual value. So what is the way I'll put a main to it, the heading to it? Probably let me call it as actual values. That is the name of the heading I'm putting, right? Or probably actual values versus fitted values. That is the name of the value heading that I'll put. And the label on the x-axis, xlab, I can very well mention it as a date. And what is the label that we have on the y-axis? The monthly Sensex values, right? So monthly Sensex values, that is what, let me call it on the y label. And probably if required I can very well plot a kind of a not a dotted line, a solid line. So LTY, the line type, I'll set it equal to 1, which is nothing but it's a solid line. So basically this plot is giving me, this is how right from 2011 to 2015 the Sensex values are moved. On the top of it, let me try to superimpose, right? On the top of it, we'll superimpose another line, probably a dotted kind of a line, using our fitted value. So that's where I'll use the lines function. Lines function will impose another line on the existing chart. So I'll say fitted of mod. I'll take the fitted value right? That is what I am trying to superimpose. But this time, probably LTY, I'll set it as 2, which is like a dashed kind of a line. And probably we'll set a different color also. Let's use a red color to plot this. So this is coming out. This is what is my fitted line. The red line is my fitted line based on the model, and the black is the actual. And what we could see is more or less there is a kind of dependency between the fitted line and the actual line. So that is where, that is the kind of a closeness or proximity that is coming out through our fitted model when we are going with the actual model. And on the top of it, I can use another function to really check the accuracy of the model. So I can use a function called accuracy of mod, which will give me the accuracy of the model in terms of different estimates. One, I get mean error. So the average error in the estimate is around 105. Whatever I am going to predict, the average error is going to be around 105. The root mean squared error, right? The squared of the error, when I take the square root of it, it is around 895. This value I need it to be as low as possible to get much accurate estimates. So here it is coming out that the root mean squared error is around 895, and probably with other models the error could be much more higher. So this is where the best possible model is coming out. Then it is showing the mean absolute error. The mean absolute error is around 730. These are the different ways of measuring the errors. The average percentage error is around 20.28%. Mean absolute percentage error is around 3.51%, and mean absolute scaled error is around 0.23. So these are the different ways of assessing the accuracy of the model. So all those things also will be obtained through your accuracy function on the fitted data. And finally, once your model is ready, you can use it for the prediction purpose also. You can use a function called predict. So use the model, which is the mod, which is the model that you have created, and for how many period. Let's say I want to forecast it for the next 3 months. I say n dot ahead equal to 3. N dot ahead equal to 3 is for the next 3 periods. I am going to use the same formula to do the prediction for the future. So what this gives is, this model gives me this numbers. So for 2016 Jan, going with the prediction, this is going to be the number for January 2016 with a standard error of around 911. For February, the number is going to fall a little bit to 25,917 with a standard error of this much. And for March, it is going to be around this with a standard error of this much. So we can very well see how the projections for the future are going to either increase or decrease over the next 3 months, and we can, if required, we can even go with a plot, right? I can even go with a plot of the forecasted value, forecast mod. I'll do a plotting where I'm going to get, this is how the numbers are going to be for the next 3 months. So basically for 2000, whatever is the next period, right, it is going to be somewhere here, and from here it looks the next month, this is the kind of a standard error. After that, approximately the number is going to be like this with the standard errors of here and here. So this is the kind of a plot that I can get for the forecast that I am making. So this is the basic ARIMA model. And just for if you wanted to use the whole data, right, the whole prices again to fit your model, we could have got a completely different model. This is the data we have used only from 2011 to 15 as a base. So we got a different model. Had you used the data right from 2010, 2000 onwards till 2015 to create the model, we could have got a totally different model. So depending on what is the kind of an input data that we are using, we get an appropriate, the best possible model which is fitting to that particular kind of data. So this is how once we come across any kind of a time series data, we can very well think of fitting ARIMA model, and it is quite comfortable to do the same using R as we have clearly seen here. If you have any further queries, you can get back to me by giving me a call on the number that I have provided below, or you can send in an email at this email address that is provided in the slide. Thanks a lot for listening to this session. Thank you very much.